Good evening. Well, it's evening here, so just take it as a generic good day to you, wherever you're at. Welcome to lecture number 11 in the Introduction to Statistics series on the Tutor Wizard. I'm Tim. Today's host, however, is Abigail, also known as Abby, and her and I are good friends. If I'm doing something in the garage, she's there supervising every time. Ragdolls are here tonight too. Don't have the camera set up. I got to get a cat cam. I really do. I've got Annie's off to the side, and Willow just popped by to say, "What the hell are you doing?" And then realized that I'm going to be talking for the next hour and a half, and buggered off. I think that's what's known as a ragdoll snub, but it is what it is. So for lecture 11 tonight, we're moving into inferential statistics, which should run out the rest of the course. So we're going to look at the basic ideas of inferential statistics in this lecture. And then we're going to slide over to the first of many topics under that subtitle, confidence intervals for one sample proportions. Of course, we'll be doing hypothesis testing for the same, and then we'll do it with two samples. We'll do the same for mean values. We'll do analysis of variance later on, and some regression analysis along with correlation. So that's what the near future has for us. Anyway, Abby approves of that, and we're going to get underway. By the way, she's not quite a pure void cat. She does have a little patch of white on her. My understanding is pure black cats that don't have any white are rather rare. It's like trying to find a female orange cat. Most orange cats are male, from what I understand. So Abigail does have a little button, and I've seen other black cats that have a few white whiskers, but a pure black is a bit rare. So if you've got one, well, you got a great kitty. They're very smart. This one is probably one of the smartest cats I've met in a long time. I swear if she had thumbs, I'd have to lock my bedroom door, because I wouldn't trust her to not get into shenanigans. Anyway, let's move on. We got a lot to talk about tonight. Let's get busy. Let's go to the next slide. So what is inferential statistics? Well, there's a lot of ways to talk about this. I'm going to keep it pretty straightforward, though. We're trying to, let's say, make educated guesses at things, at ideas, whether they're true or false, but that ultimately is what we're doing. We're taking some information and we're analyzing that information to decide, is something possible or not? There's two ways to do that. You can use hypothesis testing, of course. That's this one here. Here's your hypothesis testing. And the other way to do it is with a confidence interval. So the hypothesis test we'll get to in later lectures. Today we're going to be focusing on confidence intervals, but I am going to talk a little bit about hypothesis tests anyway, because I'm working on the assumption of how your professor is laying out the material. And for the most part, what I'm familiar with is we hit the confidence intervals and the proportion topics first. So that's what I'm basing this on. However, I don't want to leave you hanging if that's not for you. So hypothesis tests, what do they do? Well, they're going to answer a question either with a yes or a no. Either something is or something is not. Sort of like a Yoda thing. You either do or you do not. There is no maybe. There is no try. So in the language of statistics, H subscript null represents the null hypothesis. And this is usually the hypothesis that there is no change, that nothing is different than what you expect it to be. If you like cliched phrases, we could say that it's business as usual. But the point is, there's no difference from what you were expecting. The alternative hypothesis is that there is some difference. And we'll get to how we decide where that happens when we get to this little bit in a minute. So I just want to write this out. Alternative hypothesis. So this is the hypothesis that there is change. Something is different, significantly different from what we were expecting to see. Well, there's the word. What does a significant difference mean? We're going to talk about this in quite some detail. But this is usually given by the Greek letter alpha. I have more to say on this in another slide, but my point is we have to have some criteria that allows us to say this has stopped being a result that is easily attributable to random sampling variability. In other words, luck. And now the phenomenon that we're measuring is not due to luck or random sampling variability, but perhaps due to some underlying mechanism. Now I see we have ads running. I don't want to get talking here. I'm going to wait until these run out. I don't want to leave anybody behind on the initial viewing here. So just bear with me if you're looking at this or watching this video on some point later when it's just a recording. These ads are pretty, usually fairly 15 seconds at the most. This is usually one or two that are 30 seconds, but we were already through 3 of 5, so we'll just see. Now we have the Subway ad, so that'll run for half a minute, and there's probably another 15-seconder after that. And we'll get to that. Now, well, we're ticking away. This one's almost done. Only another 8 seconds to go. There we go. Okay, we're on our last one. This one's only a 15-second ad, so we'll be back on here momentarily. We're back. Okay, so I didn't want to leave that behind. So the idea with the level of significance is this sets a criteria of which we can judge whether what it is we're measuring is likely due to chance, I call random sampling variability, or perhaps not. And if it's not due to chance, then maybe there's an underlying mechanism that is driving whatever it is we're measuring. So we're going to talk about that in more detail here in another slide coming up. So hypothesis testing is about half of the ideas that we're going to talk about, but ultimately it comes down to this. It gives you a yes or a no answer. And sometimes that's not really enough. And that's where confidence intervals come in. We can answer the same questions with confidence intervals, but the confidence intervals give us a measurement of accuracy. I know my spelling's terrible. So this is usually illustrated by what's called the margin of error. We're going to beat this up tonight. But it also gives us an estimate of reliability. And I'll explain that too. And the reliability aspect is the percent confidence that confidence intervals always talk about. And that's specifically reliability is from the confidence levels. Accuracy is the margin of error. So when I'm talking about a confidence level, if we're talking about, I'm just going to scroll this screen a little bit. So just to speak a bit more to this confidence level stuff. If we're saying that we're 90% confident, we're saying that we expect that our method of analysis that starts with the sampling procedures and then with the analyzing procedures, if we're 90% confident in our methodology, that means 9 times out of 10, which is 90%, 9 times out of 10, that our interval will capture the true but unknown value of the parameter we're estimating. Now, I'm sorry, I had to start talking a bit like a professor there, but that's probably the best way to talk about this. We do have to speak the language of statistics sometimes because it's been fine-tuned to convey as much meaning as possible. So what am I talking about? Well, remember, we're going to be talking about proportions tonight. So p hat, this is the sample proportion. This is what you measured, okay? So p hat provides an estimate of the parameter. Now recall from earlier in these lectures, this is what's called a statistic, but it estimates the parameter p, or p sub 0, for the population. Now the two things will likely never be the same because the only real way you're going to ever get p hat equal exactly to p sub 0 or p null is we do a census. And that's not the point of sampling, though. Okay, so let's not get into that. My point is we're saying at 90% confidence that 9 times out of 10, our interval, which has a lower bound and an upper bound, will capture or contain the true value of the parameter, this thing. And I have more to say on that when we do some examples, because that's probably the best way to understand this stuff is to see it in action. Okay, and notice how I said that we are 90% confident that p hat correctly estimates the parameter p null. That's part of how we'll do a written response later on. So keep those words in mind. Let's move to the next slide. Okay, so this is just a little cleaner than what you saw on the previous page. When we talk about the null hypothesis, the hypothesis of no change, should we use a highlighter in this one? Let's use a highlighter. We talk about the null hypothesis. This, if you have to do a written response, or perhaps you have to select the correct form of this statement, this is what you want. Capital H and then a subscript is usually how we reference hypotheses. The zero, the subscript 0, is the null symbol. Now take note of this. Let me get my highlighter to a thinner line. That one is too, or pardon me, my pen. The correct usage of symbols, and you'll get it wrong if you don't do it this way. If we're talking about mean values, you're going to have the Greek letter mu, because that's a parameter. And we're talking about proportions, which you're doing tonight, and on the next lecture as well. It's either going to be p or p sub 0. I'll use p sub 0 here. And it's going to be equal to some value. So this isn't going to change. What does change is the structures then of the, whoops, go back there for a minute. What's changing though is the structures of the alternative hypotheses. There's 3 ways to write this, and I'm not using the equal signs in here because that's not how we teach it here, and I'm tailoring these lectures to my specific students. But again, H sub A represents the alternative hypothesis. And again, all through these, you'll notice that we are using the same parameters. The only thing that's different is the relational symbol that separates the statement from the value. The first 2 are directional. The alternative hypothesis may be that we've measured something that suggests that whatever we measured is actually evidence for a greater than relationship. The second one is a less than relationship. Or, in many cases, in many disciplines, we don't do the directional, we don't prejudge ahead of time whether something's bigger or smaller. It's either going to be equal to the value or it's going to be different from the value. Now this one here is interesting. The last one, the different from. You will see this written. This is how you're gonna, when you read the question, it's gonna tell you that something's gotten bigger. That's this one. Something's gotten smaller. That's this one. Or something's just changed, or it's different. And if it's different, then you're choosing the relational symbol does not equals. But this has an implication. That makes this a two-tailed test. And we'll get to this in more detail later. I'm just bringing you up to speed on a couple of things. So this is called a two-tailed test. And the implication is that we're going to go 2 times whatever the measured p-value is. That's usually the way we do it. The other way to do it is to divide the level of significance by 2. The end result is the same. We'll talk about it in more detail later. But for now, keep in mind, if you're doing hypothesis testing ahead of time, from what the lectures are right out, does not equals represents different, and then that has an implication when it comes to coming to a conclusion about what to do about the null, or pardon me, the alternative hypothesis. Okay, we'll get to that. It's coming up. Moving to the next slide, because we've got a lot of stuff to talk about, a lot of ideas here. I'm going to talk about this over the next couple of slides in some detail. Hopefully, I won't bore you to tears. So the level of significance, as I said, is a value that we choose that's going to delineate a non-random result from a random result. Either the result simply happened by luck, random sampling variability, or perhaps, I'm using that word specifically because we haven't got to the errors yet, or perhaps there's an underlying mechanism that's causing what we measured. Now, alpha, this Greek letter here, is the symbol for this. If you are not told what to set alpha to, the default is 5%, which is 19 times out of 20. But there's reasons that you could go to 0.1, which is 10%, or much more strict 1%. I will discuss that in more detail in a couple of minutes. Let's look at the number line I've got down here at the bottom, however. We'll use the highlighter for this one. So what we just talked about, you see right here. Here's the level of significance set at one of those values. Now, if the p-value, this guy right here, is less than or equal to what you set alpha to, there's a number of conclusions that we can make. The most important one is that we now have evidence to reject the null hypothesis. That's this one. Now what does that mean? Well, it means the result we measured is unlikely due to chance. We never say in statistics that something is certain. Everything we do in statistics has a margin of error. You can always be wrong through no fault of your own. Now, this is what I've been sort of dancing around. This is a possible type 1 error. And a type 1 error is a false positive. Now, more to say on that in a minute. Now, what happens if the p-value is greater than the level of significance? Well, then we have the opposites, the complements. We have evidence, we fail to find evidence to reject the null hypothesis. And that means the result is likely due to chance, random sampling variability. But there's always the possibility of being wrong, and in this context, that's the type 2 error, which is a false negative. Now, this is the p-value based criteria for this. The other way to do this is with critical values, which we'll talk about when we get to the actual hypothesis testing. But I'm not going to talk about that tonight. I don't want to mix things up too much. I just want to remind there they are. Okay, cool. All right. So keep this in mind. If in any context in statistics, if your p-value is less than or equal to the level of significance, you have evidence to reject the null hypothesis. If you remember that, you've got a good starting point. Now, let's go to the next slide. What the heck is this type 1, type 2 error thing I've been rabbiting on about? Well, like I said, they're false positives and false negatives. So typically, the example used for a false positive is from the judicial system. A false positive is analogous to saying, or giving the example of an innocent person being wrongly convicted of a crime. They're falsely found. The evidence has been erroneously found to convict that person. False negative, then, is the opposite, where a guilty party goes free due to lack of evidence. But there's other ways to think about this. So I'm going to give a long-winded little story here. It's a great example. It's from a really old textbook I saw probably in the late 90s, I think. So let's talk about this. Because you're probably asking, well, wait a minute. Let me flesh this out a little bit more. How do I choose whether alpha is at 5%, alpha is at 10%, or alpha is at 1%? Because whatever you choose of these is directly going to affect the chance of either the false positive or the false negative. And if it's up to you to make this decision, you want to err in the direction of least harm. Let me spin a yarn here, tell you a story. Where I'm located, we don't have any, this minuscule amount of hydroelectric. So all the electricity in my part of the world is generated from thermal power plants. And the idea behind any thermal power plant is you burn fuel to generate steam. Steam runs the turbines to generate electricity. But then now turbines use pure water, distilled water, because you can't have minerals in there because the machinery won't last. So you don't waste that. So the steam goes through a condenser circuit where colder water is circulated around the steam-bearing pipes, causing the steam to recondense under pressure, but it recondenses back into water and it returns to the boilers to generate power again. But of course this heats up the cooling water. What do you do with that? Well, thermal power plants then are built near bodies of water. And what they do is they pull in water from the reservoirs. Now around here where I'm located, there's a lake, and they pull water in from the lake. It's used to pull waste heat out of the steam cycle, and you dump the hotter water back into the lake. So if you imagine yourself in the role of environmental monitoring, that's your job. Make sure that the water is not too hot going back into the lake. If the water is too hot, then you're going to damage the environment. You'll certainly be killing life in any fairly large radius around the hot water outlet. Let's talk about what can go wrong here. If you pull up one day on your randomly scheduled visit to test the water temperature, and let's say that 50 degrees, well, that's too much, let's say 40 degrees Celsius, because we use those units around here, like every place else in the world, except two places. Let's say that the maximum outlet temperature, so as to not cause environmental damage beyond a small radius around the outlet, has to be 40 Celsius or less. And you get a measurement of 42 degrees Celsius. Well, clearly that's not right. It's not supposed to be. So what are the consequences then of that positive reading? Well, the power plant is likely going to be fined. That's a monetary penalty. Some engineers are going to work overtime trying to find out where the problem's coming from and fix it. That's the consequences of a positive result. But what if it's a false positive result? Let's say you happen to sample the water at a random fluctuation and you got the 42 degrees. Or perhaps your measuring instruments were malfunctioning. There's a myriad number of reasons for you to get an erroneous reading, and that would be a false positive. Well, how do you rectify a false positive in this context? Well, you can give the power plant operator his money back or her money back. And if the engineers worked a little overtime, well, surely they got paid for it. So there's no real harm, because even though you measured 42 degrees Celsius going into the lake, in reality, the true value was less than 40. So no harm there, really. A lot of inconvenience, but no real harm. Now, what's the false negative? So you measure the water, you get 36 degrees Celsius, that's fine. You go on your way, you're not coming back for another 4 or 5 days to do another sample. But in the meantime, the reality is the water was hotter than 40 Celsius, and that means for the next few days until you're back for another sampling expedition, you're pumping out, the power plant is pumping out water that's too hot and causing maybe not irreparable harm, but certainly long-term damage to the environment. That is a false negative. So if you want to minimize, when you choose your level of significance, you want to minimize the result that causes the most damage. Well, we noticed that the false positive didn't cause any real harm, and the false negative did cause real harm. So what happens if let's take a look at the two extremes, the 10% and the 1%. If you set the level of significance at 1%, that means you have very strict criteria to get the rejection of the null hypothesis. The null hypothesis in this context is that the water temperature is at or below 40 Celsius. Well, setting the level of significance at 1% makes it really hard to get a positive result, but it makes it really easy to get a negative result. So setting alpha at 1% is a risky choice, because if you're wrong and have a false negative, you're causing environmental damage. If you set it at 10%, now you're making it harder to get a false negative, to get a fail to reject the null, but you're getting an easier opportunity to find evidence of hot water, in other words, a positive result. So setting the level of significance to 10%, or by default 5%, these are your two choices that cause the least amount of harm. Setting it to 1% makes a false negative easy to get, and the false negative is the result that can cause the most damage. Now, in introductory statistics, this is hardly a topic of extensive testing, but it's valuable for you to understand what these things mean, because without a doubt, you're going to have to review research papers. And it's good to have an understanding of why decisions were made and how perhaps you may have done something different. Oh, hey, we got somebody online here on the chat. Hello, Obama Obama ballin' in your hood. Hello, yes. Howdy, howdy to you too. I'm just going to respond. I don't have my usual characters with me tonight. I'm pretty sure Lorenzo's busy with a few things, so I will just fire back a big old howdy doody here. There we go. Always good to have someone pop in for the conversation. Okay, so that's the whole idea behind these two things. If you end up taking more statistics, this will become almost second nature. But even if this is the only statistics course you have to take, at least now you'll have some insight into research papers that you're going to encounter through whatever discipline you're studying. Let's move on. Okay. Now, we're going to move into confidence intervals here. And I have more to say about hypothesis testing and the ins and outs of hypothesis testing as we make our way through the series of lectures remaining for us this summer. We'll just save those when we encounter them. Now, confidence interval. All confidence intervals that we're going to encounter take this basic form right here. Your estimate. Now, in this course, we're either using estimates of proportions, so that's your p-hats is what we're doing tonight, or mean values, which is y bar or perhaps x bar. What do we got here? I was wondering when's the best time to chat about the future of the website. Hosting costs have been honest lately. That is a good question. Let me bounce that one off of Adrian, and I'm just the chat question here. We'll have to chat with Adrian and Lorenzo. They are the primary drivers of this stuff, and I will have them take a look at this. So once I'm done the chat, Obama ballin' in your hood, I'll forward your question on to them and see what to do about that. And give me an idea if you want, you don't have to say exact dollars, but if you can tell us a percentage change in costs, we'll go from there. Okay, getting back to this stuff. So we have an estimate, the thing you measured, but then we have to add and subtract the margin of error. And that is this piece here. This is the margin of error. That's supposed to be an of, by the way, not at. So the margin of error consists of a critical value, which is a table lookup, times a standard error. Standard error formula is for proportions this thing here, and for mean values this piece here. The critical numbers are a table lookup. So you'll notice for proportion, I'm using Z star. That's how I do notation for this. So the critical value for anything dealing with Z for proportions, these numbers are pretty straightforward. 1.645 for 90%. 1.96 is critical value for 95%. 2.326 is 98%, 2.5, you can tell how long I've been doing this stuff's memorized, 99%, oh I missed the 1.282 down here for 80%. Those are easy because you always, okay. No, don't put your contact information in there. Why don't you send that to our email? I'm just chatting to the chat. I'm chatting to the chat. Okay, how meta. Yeah, tell you what, Obama in your... Oh, man, that's a tongue twister. Obama ballin' in your hood. Let's see what we can do. Why don't you shoot us an email at thetutorwizard@gmail.com, all one word. If you look at the, either go to our Discord, just do a search for our Discord. There's an email, there's a list of information there, and just bang off an email, and I'll have the lads take a look at what they want to do with that. Okay, let's get back to this. Okay, so when we get to mean values, we have to pay attention to degrees of freedom, which will be n-1. We're going to save this conversation until we get to this topic, but whenever we work with t, we'll always have to be aware of the sample size because we have to compute degrees of freedom. And the same thing's going to happen with chi-square, and the same thing's going to happen with analysis of variance. But for now, proportions is lovely in that we don't need to chase degrees of freedom around, and that keeps things kind of slick. Okay, now make sure you understand how to structure these things. So for proportions, what we're doing tonight, we're going to have our estimate, p hat, plus and minus the critical number. And I screwed up. Oh, no, I did not. Sorry. Well, actually, I did. This should have been a hat, and this should have been a hat. There we go. When I was typing the latex, I missed the hat. Okay, so our margin of errors, the standard error portion uses the estimated value. Yeah, p hat times 1 minus p hat. Something I said the other day, I think I said it to you folks, I may have said it in class too. Whenever you're computing the standard error for proportions, you're either going to have p null 1 minus p null, or you're going to have over n, or you're going to have p hat 1 minus p hat over n. So this is what's called the success condition. And people said yes. And this one here is the people who said no. And this is how these always appear. It's I'm stating the obvious because it's a great way to see, oh, did I screw up? If you multiply by p null, or p hat, what we're doing tonight, make sure you also multiply by 1 minus p hat, because it's always the success condition times the failure condition divided by n. Anyway, that's, I'll nag you about it later. Let's move on. We've got some things to do tonight. I'm going to get them done. Okay, how do we find critical values? Like I said, critical values are a table lookup. We're not going to chase the t-table around tonight. We'll chase the z-table around tonight. So let's look at, we'll do the 75% in a minute. Now I wrote down the easy to remember, the commonly occurring numbers earlier. If you're looking at the Z table in its entirety, I just have a trimmed portion of it here. On the Z table, at the very bottom, you'll find an infinity symbol. On most of these tables, not all, but most, if you are looking at a table where there's the infinity symbol, that is just another way of saying that's your Z star row. That's where you can get the 1.282 for 80%, the 1.645 for the 90%, etc., etc. So for instance here, if this is 95%, and it is because it said so, then this is 2.5% and this is 2.5%, because remember, the entire area under that curve has to be exactly 1. So you can see that this now adds up. We have 2.5 plus 95, which gives us 97.5, and then another 2.5, which gives us the full 1. Now I have the example here, 75%, because I wanted to illustrate how do you find the critical value if it's not a commonly occurring value, and 75% is not commonly occurring. So what you're going to do, I'm going to draw just a quick and dirty little picture here. Now remember, confidence intervals always talk about the center. I'm going to write it in decimals, but there's your 75%. Now, oh, wait a minute. Did I screw that up? Yeah, let's not do, oh, I typoed it again. Rats. Okay, let's do this. Let's make this 85%. Okay, we're going to do 85%, not 75%. Probably could have done that. You know, I see a 12.5 on there. Actually, no, we could have done that. Well, we're going to do the 85%, and then we'll do the 75%. If that's 0.85, the remaining 15% has to be shared equally amongst the tails. So we have to look, I always say, just look for do the bottom one, the far left side first. So that means each tail is 0.075. And if this is 0.075, now everything adds up. Now, this is going to, because here's our center, everything over here is negative, everything over here is positive. We have to find this value inside the Z table. And if we look, where's my highlighter here? If we look, here is almost exactly 0.075. 0.075. It's 0.0749. That's good enough for us. So how do we turn that into a z-score? Well, we need the second decimal by going up here. So it's going to end in a 4 because that's 0.04. And then we're going to come out here to this one. So what do we end up with? We end up with a lower value of negative 1.44. Well, that means over here, this is positive 1.44. These are our z values, and if you're wondering why in the confidence interval we have a plus minus, the margin of error, well, here's where your plus minus is coming from. Now, that's for 85%. Now, I originally had this at 75%. Well, that means there's 25% that are left unaccounted for. So 0.125. That is times 2 is 0.25. That's the missing amount. So if that's the case, we have to try to find 0.125 inside the table. And I got lucky on this one. My typo, there's the 0.1251, which means if we come up here, we have a 0.5, and if we come out here, we have negative 1.1. So in this context, we have negative 1.15 is our critical value. And I know at the university I've been hanging around at for the last 21 years, this is a common exam question because a lot of students find it rather challenging. So practice it. Once you get the hang of this, it's not hard. It's just getting the hang of it. And so typically with the Z table, you start with these values, and then you go inside to find the value in there. Well, what we're doing now is we're going backwards. We're starting inside and working our way out. That's how you find your critical values for the less common p-values or critical values. Okay, let's move on. Let's do some examples here. Here we have a normally distributed population that we know to usually, well, these people are kind of grumpy, but we know historically that roughly 30% of the population approves of whatever their local government does, regardless of whenever we make a study. Now we have a sample of 200 people, and that says 50 out of the 200 approving of the actions of the local government. We're going to construct a 95% confidence interval for this sample, and then we're going to tackle the idea of hypothesis testing. We'll come back to the hypothesis test part here in a minute. So let's do the 95% confidence interval. Well, let's go through here first off and see what the heck is going on. So if we highlight this, we see population is known to usually have a 30% approval rate. Okay, what does that tell us? Well, that tells me that H null, in other words, the P null, is 0.30. I need to know that to answer this thing down here, but I'm just walking through here to, label things. Now, what do we have here? This is N. That's our sample size. And this is the success count. Well, we have to turn that into a p hat. So p hat, the sample proportion, is the success count. I'm going to call that x over n, which is 50 over 200. And I chose that because we don't need a calculator to do that math. That's just 0.25 or 1/4. Okay. Let's make the confidence interval for that estimate. Well, what's our estimate? Well, that's p hat. And we have to add and subtract the margin of error. Now, remember, the margin of error consists of several things. We need a critical z, and then we need p hat 1 minus p hat over n, and this is all under a square root. Let's keep filling in the details. Now, a table lookup for 95%, this thing here, will show that the critical value is 1.96. Now remember, we have to use the estimate values here. So this p hat is 0.25, because that's 1/4 said yes. Now just what I said earlier, we also have to have those who said no, which is 0.75, or 1 minus p hat. And this was all measured from a sample of 200. And here's where the calculator comes out. So here we have 0.25. I'm going to do this in 2 steps. So what is our standard error? Let's work this out. Now, did I actually, oh, I didn't save it. Crazy man. What am I doing here? Did I save this computation earlier? I did not. Well, that makes me a bit of a knucklehead, doesn't it? Okay, well, that's fine. Thought I saved that one, but I guess not. So we got 0.25 times 0.75 divided by 200. Now that gives us a small number. Just as a heads up for those of you who aren't happy about calculator work, if you get something that's got 3 leading zeros after the decimal before the first non-zero number, you have forgot to take the square root. Simple as that. And that's what the 0.25 times 0.75 divided by 200 is 0.00094. So now I got to square root that. And now we're back to a more believable 0.0306. Now, if I multiply that out, remember bed math, got to do the multiplications first, times 1.96. I get a margin of error of 0.0600. Now, I did not plan it to work out to exactly 6 percentage points. I just got lucky. Now, this is not invalid, but it's not an interval. What you have here is a statement that you quite likely have either read or heard on the radio or TV in some news report that's talking about surveys. One of the ways I could answer this then is I could say, well, in a recent sample of 200 citizens, we found the approval rate to be 25%. With a margin of error of 6 percentage points, this sample is considered reliable 19 times out of 20. You often hear things like that in the media or read them in the published media. But this is not an interval. The interval means we have to have p hat, the estimate, minus the margin of error. I'm just going to call that m. And then we need p hat plus the margin of error. So this is 0.25 minus 0.06, and this is 0.25 plus 0.06. Well, what does that work out to? That gives us a lower bound of 0.19 and an upper bound of 0.31. And this is a 90%, or pardon me, 95% confidence interval. And that's what we needed to do to answer the first part. Now, let's talk about this second part right here, this one right here. Is there evidence the approval rating is lower than the expected value? Well, this is why we have this up here. The null hypothesis says that the typical approval rating at any time, it's a historical number, is 30%, 0.3. We ask ourselves then, where does that land in the interval? Now, remember, dead center in any confidence interval is the estimate. Here it's p hat, 0.25. The answer to the question then becomes where, if we were to put this on a number line, where do we find 0.30? Well, it's inside here as well. We can say p sub null is equal to 0.30. Here's the thing. In every case When the estimate and the hypothesized value lie inside the interval, we can't tell them apart. Any value in that interval is equally valid as the true value of the parameter. Therefore, we fail to find evidence to reject the null hypothesis. We do not have evidence here to suggest that an approval rate of 25% is significantly different from 30%. That's our conclusion. Now I'm just going to abbreviate that by saying we fail to reject H null. The reason why? Both parameter and statistic lie inside the interval. And for what we're doing in this course, this will always be the case when this happens. That's it. Now, let's look at another example. Here we have the usual successful hatch rate for some species of fish is 75%, or 3/4. We have a spawn of 500 eggs, and we find that 300 of those survive. We want to construct the 99% confidence interval for this spawn, and we're going to interpret the result. Well, what do we know? Well, let's go through here. This is an expected value. We can say that H null is 0.75, just like on the previous question. Again, I didn't give us p hat, but we can compute it. P hat is the success condition count divided by the total. So this is 0.60. Because here's n, here's n, and this is the success condition. 99% confidence has a critical value of 2.576. That's a table lookup from Z. Let's write this out. Same as before. Here's p hat, plus and minus, our critical value. That'll be Z star. And we have p hat 1 minus p hat over n. P hat was 0.6. This is 2.576. And in here, we have, what are we going to have here? I guess it's going to be 0.6. I was just thinking about what I did earlier, and I just realized, I screwed something up, but that doesn't affect you. I had an idea of where this question was going to go. It's just that it's going somewhere different. Why? Well, I'm a bit of an idiot sometimes. Here's 0.60, here's a plus and minus, and now it's calculator work. Again, I'll do this in 2 steps, so make it a little easier to follow along. 2.576. Let's get our standard error. Is 0.24 divided by 500. That gives me that, and then we need to square root that. Yeah, there we go. So this is 0.0220. And 0.6 plus and minus. Now we'll have the margin of error. When we multiply that by 2.576, we get 0.0564. So this is one result. The estimate is 60% with a margin of error of 5 2/3 percentage points. But that is not an interval. We have to do the lower bound and the upper bound. So 0.6 minus that should give us 0.5436. And when we add that, we get 0.6564. And we can say that this is reliable at 99% confidence. Now, one way to word this is we can say that we estimate that the true value of the parameter is 0.6, or 60%, with 99% confidence. But that's not usually how we're going to answer hypothesis tests, because remember, we still have this, right? We were expecting 0.75, 75%. If we put this on a number line now, I'll make a new one. I don't have enough room there. 5, 4, 3, 6, and 0.6564. Let's put this on a number line. Now remember, dead center is p hat, 0.60, but now where does the 75% fall? Well, 75% lies out here. So the null is no longer inside. We can say that the interval is entirely less than the expected value. And this is evidence to reject the null hypothesis. Whenever the null value, whether it's for y bars or p hats, or pardon me, for mu's or p nulls, whenever the hypothesized value lies outside the interval, this is evidence. We can say evidence exists to reject the null hypothesis. And this will always be the case. So you see how this is different than the previous one. Here in the previous one, both values, p hat and p null, were inside the interval, and that was a fail to reject conclusion. Here we have the hypothesized value entirely outside the interval. In this case, it's greater than, and that means evidence exists to reject H null. In other words, the null hypothesis seems to indicate rather strongly that there is something going on here. And maybe I'll redo this question next time when we do the hypothesis test, and we'll just see how small the p-value actually is. That's the one thing confidence intervals are not going to give you. They're not going to give you, hey, actual education, welcome, welcome. Welcome, folks. We're talking about, this is our first endeavor into inferential statistics. Earlier tonight we talked about the basic ideas behind hypothesis testing and confidence intervals and how to interpret various bits and pieces. And now we're just working through a couple of examples. The previous example over here was how to compute a one sample confidence interval for a margin, or pardon me, for a proportion. And in this case, we ended up with a fail to reject result. And the one we just finished now, we have evidence exists to reject the H null result because our estimate excludes, our estimate plus and minus the margin of error excludes the hypothesized value. Okay, let's carry on here. Well, I got a doozy here for you next. Come on. Come on. So lately at the university I've been looking at, what are Canadians renowned for saying? A? Well, I was looking at the chat here with Sensation Black Knight. Oftentimes it's A, but we're also renowned for saying sorry. And I noticed that, well, I was thinking about this the other day, actually. Dead giveaways for people in Canada. Oftentimes it's, well, oh, no, you after you through the door, right? Well, there's another one of those Canadian cliches. I have to think about that some more. I can't quite recall. It was one of those, you know, when you're sitting around and you got time to kill, but you don't want to do anything meaningful, so you just sort of sit there and go, do. I'm going to think about something completely irrelevant to anything I'm doing today, like, what are Canadians notorious for? Well, I think we're a bunch of wafflers. Sometimes it's like, yeah, well, it could be this, it could be that, yeah, we'll take it from there. Or good enough for me. You know, we're kind of non-committal. One of the YouTube channels I like to watch is Nick's Garage. Nick is a muscle car builder, a bit older than me. He's probably in his late 60s by now, in Laval, Quebec. And he builds a lot of old muscle cars, usually of the Dodge, Chrysler, Plymouth variety. And I have a certain affinity for that because my first car was a 1966 Plymouth Satellite. Had a big fat V8, 383 under the hood. Big carburetor, exhaust thing, made 300 and some horsepower. It was, you'd never give a 16-year-old a car with 300 and some horsepower because that's just stupid crazy. But it was a good time. Yeah, that car, you could be puddling along and 15, 20 miles per hour and then just hit the throttle and both back tires would break loose. Yeah, good times. Went through, I think, 3 sets of tires before the transmission said, I'm out of here, B. No more your abuse. Also drank gas like crazy, but when you got that size of a motor, you have to expect those things. Anyway, Nick's Garage, Nick tends to, this is what he does. He rebuilds motors and turns them into horsepower monsters. So I know today's engines, you can get a lot more horsepower from far fewer cubic inches, but back in the day, that's how you got horsepower. But one of his favorite sayings is, and we'll take it from there. It's non-committal. Yeah, okay, well, it's working out. Yeah, but you know what? Doesn't matter. We'll take it from there. So I think Canadians are quite given to non-committal answers, and we don't like to say, yeah, we're going to do this, or no, we're not going to do that. It's like, yeah, we'll see what happens. We'll get around to it. So I don't know, does that answer your question, Sensation Black? It's a little, maybe not what you were thinking. Oh, I know what you're getting at there, the old EH thing. I didn't take the bait on that one, though. Okay, what else we got going on here? I wanted to do this question. Well, here we have a 95% confidence interval. I should have said for a proportion, but I didn't. But that's not how you spell proportion. Try that again. Proportions. Okay, so what is the estimate value? Well, that's p hat. Now, how do you get p hat from an interval? Well, remember, the estimated value is dead center in the interval. So the easiest way to get that, I mean, this one you can eyeball, but whatever, you can simply take the average of the lower bound and the upper bound. So this works out to 0.30. So p hat is 30%. Almost said percentage points, but no, it's percent in this case. All right, that one's easy enough. Now what's the margin of error? Well, recall from an earlier slide, I told you, there it is, that the margin of error is what you add and subtract from the estimate. So if you keep that in mind, we can answer this question. If I know that p hat is dead center and at 0.30, what did I add to that to get 0.4? Or what did I subtract to get 0.2? So in general, you can take the upper bound and subtract p hat. So this is 0.40 minus 0.30 for the expected margin of error of 10 percentage points. So we're going to say m is 0.10. Now what is the critical value? Well, we're told this is 95%, so that's a table lookup. So from the table, the Z table, or the T, you can get this from the T table, most T tables give you this as well. We get Z star is equal to 1.96. There's not a lot of opportunities for algebra in an Introduction to Statistics course, but there are a few. And here's one of them. What is the sample size? Okay, how do we get that? Well, we have to think about this for a minute. What do we know? Well, we know the margin of error. Well, the formula for margin of error is the critical value of Z times p hat, 1 minus p hat, over n. Now we think about this. I've got all these numbers except n. I can solve for that. Let's pop the numbers in that we have. This is 10%. I know this is 1.96. I know this is 0.3. And I know this is 0.7. We just don't have n. So now we can try our best. There's a number of ways to manipulate this. I'm going to do this first. And that leads us, well, this is 0.21, and that leads us to that. So I'm going to, well, before I square both sides, I'm going to change the 0.1 over 1.96 into a single number. Not that I have to do that, it just seems like that might be the thing to do at the time. So this is 0.0510. And then we have the square root. Whoops, I want to do this a little differently. So one of the properties of square roots, when you have, oh, we got an add, okay? I'll doodle this out and then we'll talk about it when I'm done the doodling. There we go. Okay, we got, what's this ad? Oh, okay. It's another movie. What are you all about? Oh, 28 years later. Okay, cool, cool. The zombies have kind of run their course, but I guess not quite yet. I wonder what the next theme that's going to run for 20 years span going to be. I'll get another one here. What's this? Oh, tickets on sale. Something, something, something Batman. Okay, we'll get on here in a minute. It's an esports ad. Okay, cool. I see what's going on. Okay, we're back. All right, let's finish this off. So one of the properties for square roots, if you've got under a square root something divided by something, you can always turn it into the division of square roots. And that also holds for a times b as well. You can break that into square roots as well. So here we have 0.051 on the left-hand side of equality, and a square root and a square root on the other side. Let's just square everybody. I square this, I'll square this, and I will square that. Let's take this conversation over here. Now, what is point that squared? Okay, so this is going to be 0.0026, and that's pretty good. The next one's a 0 anyway, so we're pretty accurate with that. That's going to be equal to 0.21 over n. So we're going to have n 0.21 divided by 0.0026, and this will give us the wanted sample size. And we get 80.67 something something something. Now, you can't have, 2/3 of a person, so we always want to round up. It's usually with sample size computations, it's better to have one more than one too few. So this sample size is 81. And even if this had been 80.067, it still would have been 81. So we always want to oversample whenever possible. Now, what about point number 5 here? What is the 90% confidence interval? Well, we can get that, again, from looking at this. The only thing that's going to change is the critical value. We know what the margin of error is. It's 10 percentage points. changing the width of the interval as far as the percentage goes isn't going to make any difference. This is going to go to 1.645 now. That's the critical value. Let me just move this screen a little bit. So then if we want 90%, whoops, move that over there. So the 90% rescaling then will give us a new margin of error. We're going to swap out the 1.96 for 1.645. The margin of error isn't going to, or pardon me, what am I talking about? The standard error is not going to change. It's still 10%. So if we do that, what do we get? Well, it should be 1645 after the decimal, but let's verify that because, you know, silliness. Whoops, why did I do that? My trusty TI here, 1.645 times 0.1, and yeah, that's right. So now this is 1645. Yes, I know, I could have just shoved the decimal over, but sometimes I'm silly and do silly things. All right, so this is the new margin of error. So now the new interval will be the estimate, which is 0.30 minus 0.1645, and the estimate plus 0.1645. So that turns this into, that should be 0.1355. Yes, the irony is not lost on me. I had to use the calculator to verify that a simple slide the decimal left or right needed to verify that, yet I just did that subtraction in Minog, and well, you know, sometimes you just got to go with your weaknesses. And this is 4645. Okay, so this is our 90% interval. You're saying, well, that's got wider. Why is that? Well, that leads to the next slide. Let's take a look at that. Boom. It's our last slide of the night, by the way. How are we doing here? Well, we got about an hour into the trip, a little bit more than an hour. All right, so which is wider, an 80% interval or a 99% interval? This goes for any interval. And I like to explain this with an analogy. If you're fishing, here's a river, and you want to catch a fish, but you got to use a net. Which would make you more confident? Remember, these are confidence levels, right? Well, a wide net would suggest that you're more confident to catch a fish than a narrow net. So this would be the 99% confidence. This would be the 80% confidence. So it's kind of counterintuitive. Maybe I don't know if it's counterintuitive to me. Sometimes I think it is. Whatever. The point is, the relationship between the percentage of confidence and the width of the interval is this relationship here. The higher the confidence level, the wider the net, the more likely your interval will capture the true value of the parameter. We can illustrate this a little bit. Here's a wide interval. We could say this is 99%. And then the next step down that shows up is often the 98%. Then it steps down again to 95%. We can step it down some more to 90%. We can go down to 80% too, but the point is, as the confidence decreases, the interval gets smaller, because in our margin of error formula, we're manipulating the critical value. And this would be the standard error over here, which is, for all intents and purposes, a constant. So this number here is a scaling value. And higher percentage makes for a larger scalar. Now, there's two ways to change the width of a confidence interval. We just talked about one of them. You can change the confidence level. Change the confidence percent. That's one way. The other way is to simply change the sample size. Now, this one's definitely counterintuitive, especially for folks who aren't really math-oriented people. In the typical formulas, let's say we have S, sample standard deviation over square root n, or with our p hat, 1 minus p hat over n under a square root. In both cases, the sample size is in the denominator. In every case, when you have some constant value divided by a number or a variable that goes to infinity, then the overall value of this thing gets smaller and smaller. In calculus, we would say the limit approaches zero. In other words, shrinks away until it vanishes. Well, we're never going to get to that, but just a little math in there. Now, if you have trouble seeing that, you can prove this to yourself with your calculator. If you take the number 1 and divide it by 10, well, you get 0.10. And this works for any constant, by the way. I'm just using 1 because I'm lazy. If this is 0.00, well, I'm cheating. Let's get that out of there. Go away, go away, go away, go away. Let's go over 1,000. Well, now this is 0.001. And if this was over 1,000,000, 1, 2, 3, 4, 5, 6, Ladybugs at the Ladybug Picnic. Name the TV show, if you remember that one or not. So this is 0. There's your tenths, there's your hundreds, there's your thousands. There's your 10,000s, there's your 100,000s, ooh, there's your millions. So you'll notice the trend here. N is getting bigger, but the overall value of the fraction is getting smaller. So in a formula where we manipulate this, as this thing, the standard error, gets smaller, the interval has to shrink as well. So those are 2 ways to change the interval width for confidence intervals. Well, that kind of runs me out of slides tonight. I don't have anything else to go over. What are we going to do next? Next time we get together, which is likely to be Saturday, we're going to talk some more about hypothesis testing. And I am going to do the 1 sample z-test for proportions. Now that won't take too long because there's only a couple of ways that this thing can manifest itself. So then we're going to slide into 2 samples, again for proportions. And it's going to be the z-test. And I believe we'll have time for the confidence intervals as well. Oh, by the way, if you're joined, sorry, it just occurred to me that I didn't treat our rating party to who our mascot, our avatar is tonight. Today's host is my cat. I'm a cat dad to this one. This is Abigail, also known as Abby. Extremely smart cat, to the point where she had opposable thumbs. I don't know if I could actually keep her in the house because she's really smart. That cat is frighteningly smart. But she's also a great little kitty. As I was talking at the start of this discussion tonight, that whenever I'm tinkering around, no matter what I'm doing, I go out in the garage to tinker with something, she's got to be there to watch. Very interested in comings and goings around here. So yeah, she's pretty sexy. But you knew that. All black cats are. Now, let's go back over here to this. Open board, by the way, is well behaved tonight. Hasn't caused me any glitches. That's good, that's good. I was tinkering with software the other day. I think I may have induced a bug, but I think I got it fixed up. So next time around, we'll look at hypothesis testings, 1 sample z-test, it's obviously for proportions, and then we'll slide into the 2 sample proportions, z-test and confidence intervals. And to round out, we won't get to this on Saturday without a doubt, but the proportions discussion will wrap up with the discussion of chi-square. That'll be not the next lecture, it'll be the lecture after that. So this is probably going to be lecture 13, and this stuff here will be lecture number 12. That's kind of the plan as I see it right now. Now, I don't have anything set up tonight to hand off the rating party. I was late getting this stuff together. I did want to do that, so I thank you, raters, for joining us tonight. My apologies for not being able to hand you off to another session tonight. Simply didn't have time to prep that. But I will do better in the future. Usually I've got my wingman Lorenzo's our tech guy and our linear algebra guy. But I didn't get a chance to get a hold of him tonight because I got started late, and it is what it is. And I do want to talk more about nuclear, let's call it weaponry. There's a lot of mythology around how these things work. There's a lot of new information floating around out there. Let's be careful about that. That there's information out there that has been figured out through various methods of deduction by a lot of very smart people who don't have access, by the way, to secrets, official secrets. But if you piece together bits and pieces of information from the last 30 years, at least, last 30 years of open source information, things that have been leaked or declassified, and you think about it from a knowledgeable perspective, some very interesting things that a lot of people don't know. And if you're thinking about, well, I've read Wikipedia, yeah, the Wikipedia article is accurate up until maybe 1960. It's what comes after that. That's the interesting stuff. And I do plan on talking about that over the next couple of, probably Saturday. Probably Saturday, I think I'll probably dive into that a little bit. We'll see where it goes. Anyway, I think we should probably wrap this up tonight. I'd like to thank you for joining us, joining me and Abby. And I believe I'll be doing, well, let's see here. Actually, this is Wednesday. You know what? I might do another one on Friday night as well, because Adrian is really tied up. He's a very busy man right now, as he's got a hefty workload. He's teaching a great many intercession courses this spring. So it's down to Lorenzo and myself. I'll check with Lorenzo. He might want to do some linear algebra. And if not, then I'm probably going to fill in another night with statistics. So yeah, lectures 12 and 13 might actually carry us through Saturday. I'm thinking it might actually happen that way. But we shall see. Okay. Again, thank you so much. This is going to go up on YouTube as well, by the way. And if you're going to visit us on YouTube, a like and a subscribe would do wonders to help us keep this thing running. We're trying to get to a certain threshold. We haven't got all the right criteria yet to get any kind of real payback from YouTube. And the Twitch stuff's pretty minor as well. Because, well, we're not all that media savvy. The thing is, if you're good with math, maybe you're not so great with media or social media. Anyway, if you would choose to follow us on Twitch and like and subscribe on YouTube, we'd really appreciate that. I'm quite happy whenever I look at the viewing numbers and I go, wow, I got 47 people watch this thing, and I'm going, wow, okay, that's actually pretty cool. So I do thank you for your engagement, and let's leave it there. Why not? I'm going to break the stream now. You folks have a great rest of your day, and we'll talk to you very soon. Bye-bye now.